Next week,
Very good day to you all, and a warm welcome to today's webinar on the green design of high-rise structures, state-of-the-art, a collaborative effort between Structural Design Institute, most commonly known as SDI, and our esteemed partner, Civil and Structural Engineering Consultants Private Limited. If this is your first time with us, SDI is an educational institution that has a lot in store for you. We specialize in engineering covering areas such as design, construction, and software training. What sets us apart is our close affiliation with civil and structural engineering consultants, a name synonymous with excellence in the field, having worked on several iconic projects in Sri Lanka. At SDI, we are committed to the continuous professional development of engineers. So we offer CPD courses and events for those pursuing chartership or looking to enhance their skills. You can see the courses we offer through SDI here. We are focused on structural analysis and design, architectural modeling, and even some courses focused on specialist topics. What sets us apart from other similar organizations is our exceptional faculty, as our educators are all practicing engineers with extensive real-world experience, some of whom are even renowned in academia. Our next CPD course, Advanced Course on Project Management Analysis with Primavera P6, will be starting on the 25th of July. The course will take place for 6 consecutive Tuesdays from 7 p.m. to 9 p.m., covering a total of 12 CPD hours. It will be conducted by experienced professionals in the field of construction project management, offering you valuable insights. To register for the course, please follow our social media platforms, WhatsApp, or contact us at contact@sdi.lk to find the registration link. Additionally, the CPD course on the construction of high-rise buildings, conducted by 5 key professionals with extensive knowledge in construction and academia, will start on the 24th of August. For more details on this course, please stay tuned to our social media platforms and WhatsApp channel. We also offer a set of publications, including tall building guidelines for Sri Lanka and construction specifications for tall buildings in Sri Lanka, as shown on the screen with more to come. These books encapsulate our team's wealth of experience, diving deep into design and construction specifics. Today's webinar will be hosted by Professor Priyan Mendis, who holds the esteemed position of Honorary Chairman at Civil and Structural Engineering Consultants. Professor Mendis is a renowned researcher and Professor of Civil Engineering at the University of Melbourne, currently serving as the Director of the ARC Centre for Advanced Manufacturing of Prefabricated Modular Housing. With expertise in prefabricated structures, tall buildings, and resilience against various hazards, he has contributed to iconic projects like the Burj Khalifa and the Sydney Harbour Bridge. A prolific researcher with over 450 papers and 16,500 citations, Professor Mendis is recognized among the top 2% of researchers worldwide. Professor Mendis needs no introduction as a valued contributor to the industry. We are thrilled to have Professor Mendis with us today as he delves into the cutting-edge advancements in wind design for high-rise structures. His insights and expertise will undoubtedly enrich our understanding of this critical aspect of structural engineering. Before the session begins, I would like to remind you all that you are all able to engage and ask questions with our speaker through the chat box, and we will be clarifying those questions after the session during the Q&A. Additionally, note that a Google Form link is provided in the YouTube video description to register for your certificates. We will inform you all when the link is open by making an announcement on the live stream chat, so keep an eye out. The link will be open for 20 minutes, and make sure to fill in your name correctly, as this will not be changed later. Now, I may hand over the session to our resource person, Professor Priyan Mendis.
Thank you very much. Thank you very much, everyone, joining the webinar, and also those who are present here. I'm really very happy that I could be here, and then having a live audience as well, and then also welcome those who are joining from different parts of the world. This webinar. I'm actually, in fact, also thank you, Engineer Andrea, for that kind introduction, and also engineer, the engineering manager, Engineer Chatumi, also Engineer Andilini, also Engineer Chamil and the group running this, and always with our research manager, Engineer Dilan as well, who has done some work in this area. Now, again, that this is a topic that I have to say that I have presented in different parts of the world, but I'm actually presenting new material today. Some of you could have listened to me in other places, but I have really, in fact, added, as I said, some new material and slides, and especially for this important webinar. Now, just to start with, I'm calling this the state of the art. I'm going to talk about the world, where the world is, and in this area, and also the latest information. And being in the different committees, you can read there. I'm actually part of the Australian Standards Committee for loading structures. We do wind level 70.2, earthquake 70.4, 70.4, and different places, different committees. Now, with the experience I have, I want just to acknowledge my beginnings with the telecom corporate building right at the left-hand side of the screen to left-hand side of the screen to also the next one is the Eureka Tower, and also my involvement with which I will mention the Merdeka Tower. There was now second tallest building, the Lotus Tower, which unique structure, South Asia's tallest building, which really won the World Award for the last year in Singapore for the non-building category, or the best tower in the world category. And my work on the modular, precast modular type of construction as well. Those I have pioneered a number of things in that field. And I've also I'll talk about my experiences being in this field for now close to 30 years, and been various projects, including my PhD days. So we'll move on because we want to. We have a limited time, and if you like, you can put in the chat site. I'm happy to answer any question. It can be simple questions, but I think we'll leave it to the end. But if you think it's really it's a burning question you want to ask straight away, you can put it in the chat site, and we have a very good group here monitoring all that. And also thank you to the Structural Design Institute, SDI, which really does a service to everyone, really putting up these courses, webinars, and I know people around the world benefit from that, these type of courses and the webinars from Structural Design Institute. Moving on, so with the, I want to just start with, I have again, that these are things that I have done in engineering, like 1-day courses as well in Australia and also Malaysia. I've done it, and also in Sri Lanka and other places. I've given talks in other places, but 1-day courses even in those places. But the in terms of the wind engineering, it's a very important area. What I'm going to say later on is, because my focus today is on high-rise structures. High-rise structures design is governed by wind. And there are other loads, there are earthquake loads, lateral loads generally govern, which I'll say this later on again. But the wind is the most critical. And the design, that's why good to know a bit more basics of wind as well. Not just a code, not just using the code. Good to know. So today I'm going to really spend a bit of time, some basics, but I won't have, because the limited 1 hour session. We will do another course later on the year or next year, early next year, on the wind engineering itself. But I think last one we did here was in Colombo, was in about 5 years back. Myself and John Holmes, which one of the leaders in the world on wind engineering. He was here with me and invited by the CSEC at that time, by Mr. Shomal. Dr. John Holmes was here, so we were really presenting a course on the wind engineering. So coming back to this, some of the basics, you don't need to learn everything. Really takes a bit of time, but turbulence, these are the keywords. Let's introduce some keywords. By looking at this wind profile, it's pretty obvious as well. Wind speed at ground is 0. And it changes in about a bit of a parabolic profile. And you will see some turbulence. Now, if you can simply draw that parabolic line, but the turbulence occurs, and it's a dynamic load. So I'll come back to a diagram later on. And then you will see the roughness elements are there. If you think of buildings and other elements on ground, they are roughness elements. They change the wind profiles. And then the later on, after a certain height, it stabilizes the wind speed. 0 at the ground, and then it goes, and with a, let's say, bit of a parabolic profile, and it goes to 0. Sorry, not 0 at the ground, and we can see it settles down after a certain height. That height is called the gradient height. So the effect of the roughness is not there after the gradient height. These are important values for us. So again, it becomes, even the turbulence effects becomes less after the gradient height. So these are the terms that good to know, that when you talk about wind engineering. Today is a very much basics, and you will have heard lectures, but without some of these basics. I used to do some lectures on the basics as well. So the atmospheric boundary layers, and we need to check the boundary layers and turbulence. With these boundary layers, the boundary layers are where it comes with the different. This particular graph shows the wind speed versus the time, and at different heights. And you can see it settles down. It increases, and the turbulence becomes a bit less with the height of 153. Just example. So that roughness effects becomes less when again when it goes to the top of the building, the top of the buildings to at different heights above ground. I'll come back to all that. So again, I'll just skip some of that, the basics. But these are the features. You will realize already the increase, the speed with height, that the average parabolic profile changes, and that increases with height. And the turbulence you saw that turbulence, I will explain a bit later on, and it changes at each height level. Also, you will, again, you will, actually, it's probably not that important, but for you, just for the high-rise design, too much, but the frequencies of the fluctuations of the wind speed changes as well. And also the gust patterns. I'll come back to that gust later on. So don't worry about the equation at the bottom unless you want to study wind engineering. And like I had some PhD students as well doing wind engineering of buildings. Unless you want to do to that level or do high level projects on wind, you don't need to worry about the equations. But important to really look at that wind speed on the y-axis and the time on the x-axis. This is the wind. These are like a typical wind profile. It can change. And just identify some of these things you will not read in the web. So presently some material where will be very useful for you. See the 1 hour mean. So this is the dynamic wind speed profile. Wind speed changes with time, and it's not regular. You can see the waves are not regular. And 1 hour, you can have a mean. Also, what is more important now in our wind design is what's called the 3-second gust speed. 3-second gust speed means that within a 3-second period, that if you find all the maximums within a 3-second period and average those maximums, then you get what's called the 3-second gust speed. That is what we are using for like the loading codes, in the wind loading codes. I think everyone should know wind loading codes, whether you are like a civil engineer or even mechanical, doesn't matter. Good to learn the wind code. And these days, even architects want to learn wind engineering side a little bit, basics. Now, even with the 3-second gust speed, which is in the code, I'll come back to that later. Also, wind speed is measured by what's called anemometers. And again, Engineer Chamil, I will work, and with Engineer Dila's guidance, I'll show some of the work in measuring wind speeds. That's through the anemometer. The anemometer is measuring the 3-second gust speed, basically the average for 3 seconds. So that's how the 3-second came, but that's a very useful measure for us. 1 hour mean also useful, but the 3-second is the one we are using. Eurocode uses 10 minutes, but we think that the 3-second is the best. I always very proudly say Australian Wind, not because I'm in the committee, but Australian Wind Code is considered to be the best in the world. That's not because of the present committee, but it's more of the even the previous work, pioneering work done by Professor Bill Melbourne, Dr. John Holmes, that sort of people. Australian Wind Code has some of this work, which is not in other codes. That's why it's been used not only in Australia, other parts of the world as well. But then you can really, if you like, you can look at the Euro codes and also the ASCE 7, the American codes and all. But the Australian code is been very popular. So loading fundamentals, coming back to that, again, you don't need this amount of detail, but I thought I'll just present this as well. The mean, you can see the mean wind speed, but also the maximum. Maximum is mean plus the what's called a peak factor, which is between 3 to 4, and the standard deviation. So those who are have done statistics and all that would know what is standard deviation. So in wind engineering, we call it we look at the mean and then add the peak factor, which is between 3 and 4, and Australian code we use 3.7. And then to multiply by the standard deviation. You don't need all this detail, but it's good to see why we are doing all this. We need maximum values for our designs, structural design especially. So we need that, and that's why we get the mean plus the peak factor and a standard deviation. So then actually I'm just in Australian context, but it can be applied to different places. If you think of Colombo, wind speeds are not very really closely related to Melbourne wind speeds. That's why even at that time in 90s, I recommended that, like not working with Mr. Soma, that wind speeds, let's use our 1170.2 for Sri Lanka, and that's become the practice for Sri Lanka now. And so very close to the Melbourne values. Now, in this case, not to worry too much, but look at this one. Again, I have to go very quickly, but regional wind speed, they're called the return period. 1 year return period means, crudely, we can say the same wind speed will occur again within that 1 year. So that's a 1 year wind speed. So it's a 30 meters per second. Within the 1 year, it will definitely happen. But if you say 5-year return period, it will happen now, and in a 5-year return period, it will come back again. But after 5 years, so that's why the wind speed is a bit higher. If you think of going down that list, if you say 1,000 years, that means 1,000-year return period, it will only happen after 1,000 years. That's why they are becoming large and large return period. However, today I will not have time to go through everything, but the scientific definition, that's a crude definition. Scientific definition is that if you say 5-year return period, that means the 5% chance of again happening. 5-year means 5% chance of occurring in 1 year. So that means 5%, that's 20 years, sorry. So 5 on 20, 5 on 100. So 5% means 5 on 100, that is 1 on 20. That is the 5% chance of happening in 1 year is the 20-year return period. Anyway, these are scientific definitions, which I will not explain too much today. So there's a scientific statistic definition as well for return periods. It's like for $5 and all that. So so these are return periods, but that crude definition I said is good enough. So we sometimes say 1 year return period, 5-year return period, 100-year means return period. It'll happen now and then it'll happen only within 100 years. So that's a 100-year return period. That sort of crude definition is good enough for now. So this is the response to wind loading, but don't worry about all the detail. It's really we used in wind engineering what's called wind speed spectrum, and the time on the x-axis. So the time is that you can see with the normal storms and all that, it's really more towards that 3-second gust speed side. That's all I want to say. They are not too much there. And you will see the mean wind speed happens plus the gust, which are the turbulent gusts are there. So you add them up. But these are spectrums which you don't need to worry too much. If you like, you can read John Holmes' book, Wind Loading of Structures. That book, which you can even Google Wind Loading of Structures, John Holmes, as I said, is a very close friend of mine, and leading our wind code committee, he came, as I mentioned here as well. So his book is the most popular book called Wind Loading of Structures by John Holmes. And so some of that, I learned from him as well. My mentors in wind engineering are John Holmes and Bill Melbourne, Professor Bill Melbourne. There was a couple of us best. So I was very fortunate to learn wind engineering under both of them. So with the wind speed with height, talking about the equations, one common equations, all that are standard equations we use to define the wind profile. It's close to a parabolic profile. So in the zero at the ground, as I said, and then increases in a parabolic profile until the gradient height. After that, it roughly remains constant. I'll give some values. So this is another power law profile. Is the one we normally put it in our codes. It's next level of the parabolic profile. So then what happens? Then in the we define what are called terrain categories. Depends on the roughness. On the left-hand side, you can see like a sea or the coastal lines, airports, all that. The esprit of any roughness. So very low roughness. So the gradient height is lower because the roughness, the surface roughness is very low. It settles down very quickly, the wind speed. So the gradient height is lower. Other side is the terrain category 4, which is the city centers. So in this case, the city centers, the roughness is very large and the gradient height is very high because it takes large heights to really reach the gradient height of 500. So it depends on the where the building is. Usually high rises are in the city center, so it's towards bit more towards to the right hand side. Same time, a lot of engineers make this mistake. That is, for high rise, sometimes we take the terrain category 4, which is city center. But we had to take between about 2 to 3. Reason, this webinar I will not ask live questions, but now if I asked recently in an engineers forum also, I asked, but no one could answer this. But it's a very simple explanation. So if I'm designing a tall building, I would look at it depends on the height between 2 to 3. It can be even 2. The reason is that particular building could be the tallest building around that area. Those who have visited the Burj Khalifa, the world's tallest building, see that is by far the tallest around that area. Lotus Tower, if you think. It's the highest by, so when we are designing the Lotus Tower, we took about, as my recommendation, to take about 2 for the Lotus Tower. So we use that terrain category because there are no other buildings or structures of that height. So terrain category 2. So that's why we can't use city center. But if it's a medium rise building in a city center, you can use 3 or 4. So that's quite important to know that selection of the terrain category. So wind speeds depend on that. Wind profile depends on the terrain category we select. Now, once we select the terrain category, first one is a rough sea, as I said, or the open air. Again, that you can see the gradient height, which is the first column is the gradient height. It changes. Sorry, the last column, the gradient height. The ZG changes, and again, as I said, 500 for the city centers. Depends on the code. Some codes have different values, but roughly you should know why the gradient height changes because it's the roughness in there. I'll skip this one. So there's a turbulence intensity graph in our Australian code. Height is there, and you can see the turbulence intensity again, because as I said, the surface roughness changes, and it really, if the turbulence values becomes becomes lower. But Australian code, one of the changes, I was part of that team, we made this change. We introduced another terrain category in between called 2.5. So because people used to interpolate from between 2 and 3, so we said, why not? We put 2.5, and we have an extra column as well. For many cases, we can use even 2.5. This is a chart given in the code, turbulence intensity. The height versus the turbulent intensity depends on the terrain category I mentioned before. City centers on the 4 side, and the open, like the airports, rough seas, all that, oceans are terrain category 1. Others are in between. Now, coming back to that, the static versus dynamic. So static on the left-hand side. The static is where you are used to this equation. Force is equal to stiffness times the displacement. That's a basic equation we all learn for statics. That's on the left-hand side. You can draw your parabolic wind profile. You can find the wind forces, and then you can apply them. So force is equal to stiffness times the displacement. However, once this is important, the wind in especially high-rise structures is dynamic. You can't just say static. So the dynamic means you have to introduce two new terms, the mass times acceleration, plus also you need to include damping, because dynamic means the wind speed just changes, not static. So you need to introduce the mass times acceleration is called the inertial term. And the damping times velocity, the next term, called the damping term. And the third term is same as statics, stiffness times the displacement. Computer programs calculate all this. However, we need to know the basics. So the inertial term is quite important. Later on, I'm going to say this. If you want to reduce the dynamics, we put a large mass on top. So when you put a large mass, I think it becomes obvious as well. You can reduce your dynamics of the wind, the dynamic movement. So that's the inertial term. You're increasing the inertial term. You can increase the damping term. I'll come back to the damping. Today, I will not have too much time to explain everything about damping. Damping term means, that is, if you have a certain excitation, if you excite, the damp, if it's highly damped, it will come to zero very quickly. Like this, sine wave comes very quickly to zero. That's the damping, very high damping. So if it moves, that you can also imagine, if it moves very quickly, come back to zero quickly, that means damping. So that's the damping term. Damping is low. If damping is zero, it keeps on moving from this side to the other side of the. So that's sort of damping term. And damping values are given in the standards. Today I will not explain too much on that. I'll leave it to a longer session, a day session. So inertial term, damping terms, and the stiffness term. So always have to consider the dynamics. Eureka Tower, again, one of the projects that I got involved, the Australia's tallest, is now it's overtaken by another building next door by about a few meters, but it's a unique building. I have at the next slide, I'll show why it's unique. So with I was really helped them with the wind design and also the high strength concrete elements, all that of my work went into this building. So again, what we do in structure systems today, as I said, that's overview the lecture or a webinar. Structures with outriggers. Outriggers is one of the best inventions we had. Why we can have all these very tall buildings is due to two things now. The two things are the one is the high strength concrete, which again, some of my rules of high strength concrete rules went to the Burj Khalifa type of project. So high strength concrete really, because of the strength, we are now going up to about 150 megapascal for high-rise buildings. I was asked to look at a pre-feasibility study for a 2-kilometer building. A few years back, I was asked to comment on the material. So I was suggesting 200 MPa for that. We know how to do that, how to make the concrete. So that's the high strength concrete. The other one is outriggers. These are the outriggers. This is how the outriggers work. You have a core element. Core is where most of the wind is, about 95% of the wind is resisted by this core element. This is the lift well, where the lifts are. So we have a very stiff lift well or the core, normally concrete. And this core element, usually at the bottom, have high strength concrete, and it can be lower at the top. So the wind speed you saw, this is like a cantilever. Tall building can consider to be a cantilever, right? So cantilever with the cantilever loads coming down with the, so it's like a cantilever. You will know the maximum moment is at the bottom. Right? Cantilever is like a maximum moment is at the bottom, zero at the top, maximum at the bottom. Shear forces are also maximum at the top and the, maximum at the bottom and zero at the top. These are like a cantilever, right? So consider like a cantilever. So the base moment, bending moment is the most highest and the base shear is the highest. Those two are the very key factors we need. Moving on, what we have done now is to take a column outside and then joining that with what's called outrigger. Now, simply I have lectures of separate lectures for this, but today just to show something, right? Now, rather than one person working, right? One person working, if two people work together, right? It works better. And because you share some other, so the core moment is taken out a bit. Due to that, so outrigger column, very simply putting, I will not go into detail today, but push and pull, put some compression on the outrigger column. And from that, you have this additional moment resistance coming from that column, taking that compression and liberate tension in the core element. So I'll leave that to another day. But so this, how it works, you can read actually even some of my lectures could be in the web, but I will not explain today. But outrigger is that joining that. I'll show one example later. But that's really a key for us to design some of the tallest buildings. Every tall building in the world, tallest buildings have these sort of outriggers, but except for some special plans, which I'll mention later on. Then what we do is we put a like what's called belt truss for all the columns to work together to help that outrigger column. So these are very common. That's why we can design very very tall buildings due to these outriggers. And what outriggers is doing is like a hat like that. You can see releases a bit of the core moment, take out a bit of core moment. So core can be reduced, the sizes and all. This is something that, I'm again proud to be part of this initial stages of Eureka Tower. The developer of this building, it's a success story, it's probably the only one, then a lot of people appreciate this. The developer was the architect. So the engineers were the company that I used to work for at the time, like that, Oricon or the Conrad Wagner. But I was at uni, but I was still working with them on this project. So what we did was we said one side is a bit weak, around that area, the north-south direction. We couldn't satisfy the requirements, so we had to put outriggers. Now this why is unique. Outriggers normally are at about 2 or 3 levels. For this one, we put outriggers at each level because they are the separation of the apartments. Because architect was the developer, we could put outriggers at each level. That really improve the efficiency of the building. Because if you put a full height outrigger, so normally you need about full height, very steep, and you can't put it anywhere else. You need to put in plant rooms or machine rooms. But in this case, smartly put between the apartments, so we could put outriggers at each level. Anyway, I'll leave it like that. If there are any questions, I'm happy to answer. Shanghai Tower used to be was second tallest, but when the Merdeka is open, this will be the third tallest, 632 meters tall. I'll have some slides on Merdeka building, which is 679 meters. So this is the, until the Merdeka is open, this will be the second tallest, 632 meters tall. In this one, like I had some involvement through the Victorian government because there was an agreement with them for Victorian government to help in the high-strength concrete side. I got involved in the concrete side, not on the wind side, but on the university work. I know them well also. So what they did was really very difficult task. they change the wind pattern, reduce the wind loads. Wind loads are the key. So reduce the wind loads are a key. And the reducing wind loads means so they rotated at every story. So to minimize the load from the wind, rotate at every level by a small decrease. So again, doing this, we can reduce the turbulence. I'll come to vortex shedding later on a little bit, but I'll go through a bit quicker. Vortex shedding, that's turbulence. Reducing turbulence is a key. So we call it what's called confusing the wind. We don't allow the wind to really settle down. So in this case, by rotating every flow, really upset the wind. If you upset the wind, actually, in fact, it reduces the wind effects. Normally, it's the other way around. If you try to upset people, they become, right, more active and more turbulent, right? It's a little bit other way around here. I have these stories I'll tell you another day, but not today. But some of these turbulent stories. But anyway, this is the Shanghai Financial Center. In South Korea, I'll run through very quickly. Incheon Tower, what they did was, we call it like wind engineering is a key for tall buildings now. We spend time on different shapes and all that. So this is the Incheon Tower, South Korea. Had some slots there. You can see to reduce the wind forces through this turbulence action. 1 kilometer tower, I was again proud to be involved in initial stages. We did lots of work at Melbourne University and trying to shape up that and work on this, having slots to reduce like that, the wind flow through the slots. That work we suggested by doing compression fluid dynamics work. These foundations, they put $150 million in Dubai, but then the world financial crisis came, 2008, if I remember correct, and everything stopped. It's worse than the Sri Lankan financial crisis, which really only Sri Lanka it was confined to that. But in the world, it's world level. So Dubai, affected a lot. They stopped the construction of this. The $150 million is under the sand still. Never know, one day it will come. So that's okay. We could achieve something as a team. Taipei Financial Center, I told you, by putting a very high mass on top, you can reduce the dynamics. That's what is done. You can go there and see this big mass as observation day. So maybe you can go your next holiday to see the Taipei Financial Center and see this, the observation, like a very large mass on top, which reduces the dynamics. Also, they had rough corners. As I said, confusing the wind, having rough corners, you really also reduce the turbulence. It's all about reducing the turbulence in wind. Simply, if I put it like that. So these were about 3 weeks back, I was, those who have seen this photo as well. But Merdeka is going to be the tallest. I was very proud to be involved in certain work. I was there in the workshops from the beginning because architect was from Melbourne as well. The worst place got involved in this. But I was really gained from that experience. But I didn't get involved in everything. But in the wind design, I was not involved, but I got familiar with this one. I was more of the predictive side of things. I got involved. But really very proud that Mr. Tenku was the project leader himself. Appreciated my input to this field. Second tallest, 118. Will be open only next year. If you go there, you can only see from outside. I had a chance to go to the top. But so this is the building which really no need to read from there. But that's a building with different heights and different consultants got involved. And I was very, one of the things that I really gained from that, sitting next to Les Robertson, which I consider to one of the best in the world, who designed the World Trade Center at that time. And he was there beginning and he told me stories about World Trade Center and everything, but I will not have time to say today. But then he passed away about 3-4 years back, lived till about 90s. His wife's team will be presenting in the next AWH conference this work that they have done. She's also a structural engineer, well known to us. So this when during construction, the Merdeka Tower. So this is quite important. Those who are listening in the web, I would say seriously, please, if you're copying any of these slides, you need to get permission to present. I was part of the team, so I'm allowed to present. But if you're anyone presenting these slides, I had to get permission from the PNB developing team because there are some sensitive, could be some sensitive information. Happy to present today, but this is also from the ICE Malaysia Institute of Civil Engineers presentation. They presented this material. Now, with this is where you will see the structure. This is the concept stage. All these systems were considered. And initial workshops, I was also present when we talk about different concepts. We had Peter Irwin from our WDI Consultants, was the leading wind engineering consultant. Wind tunnel, they got big wind tunnel in Canada. They did Burj Khalifa, they did Shanghai Tower, they did Merdeka 118 as well. So they are the leaders. Our WDI, Peter Irwin, well known to me as well. So he was presenting some of those ones. But the structural group, especially Les Robertson and Robert Bird group from Australia, they were doing the initial structures. In the Arabs, Malaysia was the local consultant, later on joined. So in this case, final is this one here, first one. So you can see the different concepts were considered, different shapes of the building was considered. And this is called that's why the structural wind engineering, I don't know if anyone else have mentioned, but that's the word I've given, structural wind engineering, which is we need to know wind engineering and the structural both if you want to design these ones. And the work I have to appreciate CSEC and Mr. Shoma's work as well, structural wind engineering side. So in this case, this is the final concept and the shape. So this is called aerodynamic shaping now. That's a key in tall building design. And you can earn a lot of money if you can really master these ones. But very little we get paid, but some of these wind engineering consultants get paid a lot. But in this case, aerodynamic shaping means you're reducing the wind speed. In this case, I'll introduce that later on. But in tall buildings, the difference between tall building and normal buildings is drag force. It's called the drag force. And the other one is crosswind. Vertical is movement is crosswind. So you have movement on the like parallel to the wind as well as the perpendicular wind. This crosswind action could be higher than even the along wind action. Today I don't have time to teach all that. But look at the along wind and crosswind actions. So tall buildings, normal buildings, you don't worry about crosswind. But tall buildings, crosswind is a key as well. So you need to reduce the crosswind. So what we do is, like now, next time when I do a longer course, I will maybe do it in December, a longer one. I will really like now talk a bit more about the drag forces, crosswind, how to reduce them. I had students looking at. So Merdeka 1, again, please don't copy this one, anyone in the webinar. The office floor plan, this is the office floor plan here. In this case, these are mega columns. There are many mega columns being put in there, and the outrigger system. Mega columns and the outrigger systems are the in joining. That's how the structure system. It was very weak in the east-west direction. I know that in some of the workshops this was discussed in detail. East-west direction was weak. So Les Robertson himself came up with the outriggers from joining the mega columns. As I showed you before, core, the middle structure joining the outrigger columns outside through outriggers to make mega columns outside really gave the stability to this Merdeka tower. Don't worry too much about that. These are the outriggers, both directions. So the both directions and the east-west direction was the most critical. East-west is here. East-west direction, you can see more mega columns being connected through the outrigger systems. And the north-south direction was all right. After the analysis was done, north-south east-west had 3 outrigger levels. If I remember correctly, here at the middle level, bottom, and the top. But the north-south direction, the initial designs had 3 outriggers, but with Mr. Les Robertson's involvement, the one of the outriggers at the middle level was taken out. Huge cost saving by doing that. This is the kind of optimization you can use. So optimization is a key. Now this is the first time I'm presenting some of the Merdeka information. So that's where the building is with the, skip that detail. Looked at, see the east-west structural section, outriggers, you can see the outrigger locations. This north-south outrigger, middle outriggers were taken off in the final. Getting to the Jeddah Tower. Jeddah Tower is going to be the world's tallest, 1 kilometer tall, and CSEC was invited to by one of the Chinese builders to join their tender. Not sure if it starts again, when it's going to start. It stopped and started. 2012, I think, started. Now, and there were some other issues, political issues to financial issues to all that, and the COVID came and all that. So this got stuck. I heard it's going to restart, not haven't done that. It's going to be 1 kilometer tall, higher than the Burj Khalifa. See Burj Khalifa where it is. And then see the Burj Khalifa is 820 meters tall. If I remember. It's going to be about 1 kilometer. The structure system is not outrigger system, mega walls. I'll show a plan later. Mega wall system, like the Burj Khalifa, similar to the Burj Khalifa. In this case, SKM designed the Burj Khalifa, they got involved in this similar system they suggested. And in this case, mega walls, 3 mega walls are shown there. See the confused in the wind. So if you have symmetrical building, you get the turbulence effects, a lot of turbulence effects, and wind loads can be very high. These are the things I want to really mention in this webinar today. You need to really go and do these things in tall buildings, especially for a not 2-story building. No point spending a lot of time, but still wind is important. But when it gets to high rise, wind governs everything. So we really need to do these things. In this case, confusing wind is that as I said. See, it's unsymmetrical, different directions. So that way the wind loads were reduced. That's optimization we normally do. We also call aerodynamic shaping that we saw. These are mega walls. So this initial construction, see the mega walls being started to construct. This was 2013, if I remember correctly. They bought these ones. It's gone up to about this level, I think it's 43 level. It's very slow. That is the brand new, as I said, mega walls, triangular area at the middle, and then mega walls. So sort of outriggers, but joining the mega columns and there. So that's the system in Burj Khalifa and Jeddah Towers. Types of wind design, and the 3 wind types of designs. I'll run quickly a little. The types of wind design, so the types of wind design, the environment wind studies, that is what we do is that we have 3 types of wind designs. the wind loads for the structure. That's what's very important. Calculate the wind loads on the structure. I'll start from the top. Environmental. Having a tall building means like you are changing the environment, everything. Like it's like building a city. That's why the environmental wind studies have been done, looking at the environment. So we do what's called environmental wind study. Sometimes we do air pollution studies there, all that. That's called the environmental wind study. These are all done through wind tunnels. I'll come back to that. Second one, cladding is the external phase. So the cladding, external phase, is the wind loads for the facade. And the outside cladding is like external phase. People identify us through looking from outside. Similarly, the buildings are like the outside cladding is quite important. So that cladding wind loads are, the first cladding feels the wind load. So we need to look at the wind cladding loads as well. Codes are there, but to give crude values, that's why we need wind tunnel studies that I'll come to that. So these are the three types of wind tunnel studies we do. Design criteria same as normal. Look at the stability, which I call 3 S's: stability, strength, and serviceability. I will not go into the design side too much today. I will not have time. It's more of the wind loading side and the design, the loading side. Then what we do, there's a SDI document, a very good document on tall buildings, have a bit more detail, and some of my papers have some more detail on this. But the drift is very important. The total deflection also important. To find the total deflection, you see height divided by the displacement. We say 500,000. There are no fixed rules in the world. There are no codes, proper codes. I think one of the first is that SDI document on tall buildings document, which really anyone around the world can really ask from SDI. That book have some guidelines, but these are no fixed guidelines. So it can be 500 to 1,000, we say, the height divided by the top deflection. But more important is what's called the wind drift. This is the one which is more important. Drift means the displacement difference between the two stories height, between the story height, divided by the displacement between the stories. That's to say 200 to 200, 400. We say generally 5 to 15. Depends on the project, depends on the design, right? So 5 to 15 is, let's say 10 millimeters, you can say 10 millimeters or so. That's the reason wind drift really is another very important governing criteria for tall buildings. Other one is, I'll introduce later on, the perception of motion. But sorry to go back, but the wind drift design, the reason wind design is very important, the cladding. When you fix the cladding feels the difference in deflection between the stories, not the total deflection of the tower. So the wind drift is very important. Also the acceleration, which I'll come to that. Focus on the number A, but don't worry about B and C now. So especially for the cladding and the interior partitions and all that, wind drift has to be limited. So you need to come up with that number. That's the interstory deflection. And then I'm running through very quickly these ones. Compression fluid dynamics have changed the world for the, changed the world for the, in having for the high-rise designs. Compression fluid dynamics, the CFD. And in this case, the CFD is based on this, again, theory. Unless you want to go deeper, don't worry about that. But famous Navier-Stokes equation, and based on the Newton's laws, we studied this a lot. But again, don't worry about the numerical methods. But so in this case, the CFD means compression fluid dynamics. Solving the Navier-Stokes equations using the numerical methods. That's what we do in compression fluid dynamics. Compression fluid dynamics has changed the world in terms of high-rise wind design. And it's still evolving. Wind engineering on the left-hand side, and the compression fluid design. Compression of fluid design for any fluid. Aircrafts are designed We have been doing aircraft forever, for a long time, the computational fluid dynamics. But computational wind engineering is a combination between wind engineering and the computational fluid dynamics. So basically, that's what we are using for highrise. So then we need to look at what's called the fluid structure interaction. And fluid structure interaction, we have a computational fluid dynamics model, and we put the loads, and then we look at the deformation. So fluid structure interaction means wind node is a fluid. The two fluids are the wind, and the two fluids, the wind and the liquids or the hydraulics, the water and all that are the fluids. In this case, fluid applies a load to the structure deforms. Because structure deforms, the loading gets adjusted. This is called a fluid structure interaction. Very important to model that. We call it FSI. We don't need to model for every building, but FSI is quite important. Just remember that today is not a lecture on CFD, but I'm happy to talk about that topic on another time, computational fluid dynamics side. And so FSI is quite important, but we don't need to do for everything. Lotus Tower, we did some analysis. Thank Dr. David Mohti for doing this work with me. And for the Lotus Tower, we did some very new work for the world, looking at the FSI model using Fluent. We use to really look at, see the mass being there. And we, first time in the world, we modeled the accelerations and we compared the wind tunnel test. And they were very close. So, but I haven't seen for any other building in the world, acceleration has been calculated